Good evening. My name is Hamad Ahmed, and I am here to present our research titled Comparative Analysis of Machine Learning Method for Enhancing Sleep Efficiency and Prediction. Firstly, let me introduce our team involved in this research. Myself, Hamad Ahmed from the Department of Biosciences, and Dr. Muhammad Umar Khan from the Department of Electrical and Computer Engineering, along with Dr. Maliha Azam, also from the Department of Biosciences. All of us are representing ComScience University, Islamabad, Pakistan. Our combined expertise spans biosensing and engineering, enabling a multidisciplinary approach to our study. Let's take a look at our roadmap for our presentation today. We'll begin with an introduction. Next, we'll articulate our research objective to give you a clear understanding of our goals. Following that, I'll walk you through our methodology. We will then explore our results, and finally, we will wrap up with the conclusion. And at the end, we can go ahead with the question answers. Let's begin by understanding what we mean by sleep efficiency. Sleep efficiency is the ratio of total amount of actual sleep time to the total time spent in bed. This metric is essential because it's not just the duration of sleep that matters but the quality of that sleep. Why is this important? Because sleep isn't just a passive activity, it's an active restorative process. Measuring sleep efficiency is crucial since it correlates directly with restorative benefits of sleep. When we achieve optimal efficiency of sleep, we ensure that our sleep is both adequate and restorative. This in turn promotes better physical and mental health. It can enhance our daily functioning and improving our overall quality of life. It's about waking up feeling refreshed and ready to face the day's challenges. Recognizing the critical role of sleep, the World Health Organization has identified sleep as one of the most pressing health challenges of our time. The WHO statement is clear on call for the urgent need to address sleep-related problems. They acknowledge that sleep quality has a profound impact on a wide array of health outcomes, from cognitive function to metabolic health. This underscores the significance of our research and motivates our pursuit to understand and improve sleep efficiency through the use of machine learning models. The primary goal of our research is the practical application of machine learning techniques to accurately predict sleep efficiency. Our approach analyzes various lifestyles and biological factors that we believe could give us deeper insights into sleep patterns. To achieve this, we're tapping into power of statistical algorithms to model the interaction between key variables. These includes age, gender, different sleep phases such as REM sleep, deep sleep, and light sleep, as well as alcohol and caffeine consumption, smoking status, and exercise frequency. Each of these can tell us something about how we sleep and why we might not be sleeping as well as we could be. Understanding these interactions help us identify patterns, the hidden threads that tie our habits and biological characteristics to the quality of sleep we experience. By predicting these patterns with machine learning models, we aim not just to understand but improve sleep efficiency, offering potential actionable insights for individuals looking to optimize their sleep for better health and well-being. Now let's talk about how we approach this study. Starting with the data, we begin with the sleep efficiency dataset that we acquired from Kaggle. The dataset comprises 452 entries and 15 distinct features. The features provided us with rich data points, including the demographic details like age and gender, sleep stages such as REM, deep sleep, and light sleep, lifestyle habits covering caffeine and alcohol consumption, smoking status, and exercise frequency, as well as key indicators like the awakenings and overall sleep duration. Next, we have the pre-processing step. Missing values were imputed using the k-nearest algorithm to ensure completeness, normalized the data for uniformity, and selected relevant features to focus or analysis effectively. Once the data was pre-processed, we employed a variety of statistical methods and advanced visualization tools for analysis. We used Python libraries such as matplotlib and seaborn to create histograms, box plots, bar charts, and correlation matrices. These tools were invaluable in allowing us to visually parse the complex relationship within the data, revealing the underlying patterns and insights that would guide our predictive models. To ensure that our models were well trained, we divided the dataset into two parts: 80% for training while the models learn from the data, and the remaining 20% for testing, where we assess how well the model perform on unseen data. We applied four machine learning models to our pre-processed data: linear regression, decision tree, random forest, and gradient boosting regressor. These models were chosen for the diverse approaches to regression tasks, allowing us to cover a broad spectrum of predictive techniques. In terms of evaluation matrices, we looked at R squared, which measures the proportion of variance in the sleep efficiency that our models could explain. Additionally, we considered the mean squared error, which quantifies prediction errors. Lower MSE values indicate that our model's prediction are closer to the actual or observed values, and student t-test for linear regression. Together, these matrices gave us a comprehensive view of each model's accuracy and the magnitude of any error in prediction, allowing us to identify the most reliable model for predicting sleep efficiency. Now, let's unveil the results. Now let's look at the results. First, let's see the key factors that influence sleep efficiency. Here we present the key findings from our correlation analysis, focusing on the impact of different sleep stages on sleep efficiency. The correlation on the right provides a visual representation of how each factor relates to sleep efficiency. So first of all, let's see that deep sleep percentage shown in the correlation matrix has a strong positive correlation with sleep efficiency of 0.79. This means that deeper you sleep, the higher your sleep efficiency. On the opposite side, we see a strong negative correlation of light sleep percentage with sleep efficiency, which is minus 0.82. This suggests that increased periods of light sleep may not be as beneficial and could actually be indicative of poorer sleep quality, as it potentially replaces the restorative deep sleep. Now, let's take a closer look at how age and gender play into sleep efficiency. This graph on the left shows us how sleep efficiency changes as people get older. You'll notice two lines, one for females and one for males. The dotted line is for males and the straight line is for females. So for women, there's a noticeable uptick in sleep efficiency when they reach their 50s. But for men, the pattern is a bit different. Their sleep efficiency seems to get better in their 60s. So it's a bit of delayed improvement compared to women. When it comes to caffeine intake, we observed that the impact of caffeine on sleep efficiency is minimal across different consumption levels for both men and women. Well, this is an interesting finding as it challenges the widely held belief that caffeine substantially impairs sleep quality. Although individual sensitivities to caffeine can vary and are not captured in this overview, what this indicates is that the relationship between caffeine intake and sleep may be more complex than a straightforward cause and effect, and other factors may play a more significant role in determining sleep quality. In our exploration of lifestyle factors affecting sleep efficiency, two significant negative correlations emerged: alcohol consumption and smoking status. As you can see from the box plot in mid, sleep efficiency decreases with increased alcohol consumption. This pattern persists across various levels of intake, suggesting that alcohol might be disrupting sleep architecture or the ability to maintain deep sleep stages. Well, turning to the right, we compare sleep efficiency between smokers and non-smokers. It's evident that non-smokers generally report higher sleep efficiency. This finding aligns with the understanding that smoking can negatively impact sleep, possibly due to nicotine stimulant effects or the health complications associated with smoking. These insights are crucial for public health messaging and individual decision making related to sleep hygiene. Now let's compare the results of machine learning models. The table here summarizes the performance of each algorithm. As we can see, while other models perform admirably, the random forest algorithm provides us with the most reliable and accurate insight for our specific datasets and research objective. It achieved the highest R2 score of 0.8569 among the contenders, which included linear regression, decision tree, and the gradient boosting regressor. The R2 score close to 1 indicates a strong ability to predict sleep efficiency based on the features we analyzed. Furthermore, the random forest model had a mean squared error of 0.0027, comparable to the gradient boosting regressor and significantly lower than the decision tree. This lower MSE value is indicative of the model's accuracy in predicting sleep efficiency, making fewer errors in its predictions compared to the other models. To summarize our journey through this research, the results have illuminated pathways to enhance. By understanding how factors like smoking, alcohol consumption, and exercise impact sleep, we can make better choices to improve our health. We've seen that the applications of machine learning models, particularly the random forest algorithm, has enhanced our understanding and prediction of sleep efficiency, providing us high levels of accuracy. Looking ahead, we plan to expand our dataset and experiment with various machine learning techniques to refine our predictions and insights. The ultimate goal is to inform better health advice and treatments for individual needs, moving towards a future where healthcare is increasingly personalized. I would like to thank you all for your attention during this presentation. If there are any aspects of the research you'd like to explore further or questions you might have, feel free to reach us out. Thanks.